unfortunately I can't do that quite yet. You probably are aware that there was a major disaster in the MSC building over the winter break, that the storm drain ran into the basement of the building, which inundated UCR's clean room. And so, especially Michelle right now has to go to UCSD like every other day to do her work over there, and then might have to late. But we're trying very hard to catch up, and so I hope that we have an exam by tomorrow, or at least by Friday. Okay. Then the subject matter is still that we have to do kinetics here. We have to understand how fast reactions are. And in trying to do that, we first of all realize that we want to have a measure for the speed of the reaction, which we call the rate of the reaction. There are different reaction rates defined. We always need to make sure that we know what we are talking about. The confusion will come about very soon, very easily. That we might talk of the rate of the production of something, or the rate of the consumption of something, or the rate of the overall reaction, which is normalized by the stoichiometric coefficients, and hence depends on the how you happen to write the reaction. It might have sounded trivial so far, because we always had first order reactions and unimolecular reactions so far, where we have always a stoichiometric coefficient of 1, and so we didn't see where all those ones were, because 1 over 1, who cares? But then we'll change in this session, and it will change for the remainder that we talk about kinetics. And so now we open the floodgate for all those kind of confusions about the numbers. So you remember in electrochemistry there was always a minus signs where there's one too many will be reasonable. Here in kinetics, it's always those stoichiometric coefficients which are there to set you off, and for which there's really no good reason where they are, and they aren't because of weird conventions, but they are still there. So we were talking unimolecular reaction, and from unimolecular reaction we realized that the power of the exponent here is 1. If it's only one molecule, then one molecule has a rate of decomposing under otherwise identical circumstances, which is constant, doesn't depend on how long it lives. The molecule doesn't know its age. But today, we are going to look at different kinds of reactions. So today, let us look at a reaction where we assume that we have two different molecules reacting with each other. If we have those two different molecules reacting with each other, then we can wonder what is going on over here. And we'll find that we have maybe a certain rate of the reaction if we have the molecule, if we have one red and one green molecule in that. So let's call this rate over here 1, and whatever units it turns out to be 1 if I have one red and one green molecule available. And as rate comes about, we realize the Arrhenius equation. It comes about with a certain likelihood that those two molecules will hit each other, running around in a box forward, backward, bouncing against the walls. At some point they will hit each other, and then they have a chance of undergoing that reaction. That will be the pre-exponential factor. And how big the chance is that they undergo the reaction, that depends on the ratio of the kinetic energy to overcome the activation barrier and the size of the activation barrier. And the kinetic energy is of course given by kT, and so it is the activation barrier divided by kT. Now if I happen to have two red molecules in this container, then this red molecule can hit this green one, or that one can hit this green one, and quite logically then the reaction rate will be twice as big if I have two reds and one greens. just 2 different times the chance for the reaction to occur, because there are now 2 red molecules which can possibly hit the green one. Now if the other molecule were green, the same argument holds true. I'll get 2 times the rate for that, because now the one red molecule has 2 chances of undergoing the reaction by hitting this green one and by hitting that green one. So 2 times the rate of the reaction which we had in the beginning. If I have 2 of each kind, then this red can hit this one chance, this one can hit this one, 2 chances. These 2 can hit 3, these 2 can hit 4. So we have 4 times the chance, 4 times the rate for the reaction to occur if we have 2 of each species. And then we can of course go on and on and on in this way and say if we have 3 of the red ones and 1 of the green ones, then the green one can hit one red, the other red, and the last red, and then we get 3 times the chance. So what you see immediately from this one is something which was probably not new for you anyway. If I have a bimolecular reaction, if I have a reaction which depends crucially on molecule A hitting molecule B, then the likelihood for that reaction to occur is given by the product of the concentrations, the product of the number of the molecules which I have present. So in this case, the utility 6 and so on and so forth. Okay. So what I've figured here now is that the rate of my reaction is given by some K times the concentration of, let's call these ones here A, and let's call these ones here B, times the concentration of A, times the concentration of B. So a bimolecular reaction has the rate law, which is in A and in B. It's a product of those 2. And this one here, the rate is of course the change of the concentration of A, and A is being consumed in this reaction, so it's minus in front of that. It's only one of them, so I don't need to divide by anything because it's 1 by dt. And it would be also, of course, minus dB by dt. Now, if I'm looking here, where do we have the powers? Where do we have the powers over here? That is always to the power of 1, correct? X is the same thing as x to the power of 1. So we can always write it, it's to the power of 1. And then I add up all those powers over here, and that will give me the order of the reaction. In this case, 1 plus 1 gives 2, so I have a second order reaction. A bimolecular reaction step leads to a second order reaction. It's not the same thing to say it's a second order reaction and it's a bimolecular reaction, because the second order part is a consequence out of the bimolecular one. But not all second order reactions are necessarily bimolecular. So if I have bimolecular, I know it will be a second order reaction. If I have a second order reaction, I need to have very controlled conditions to guess from that whether it was bimolecular or it wasn't. Okay. Next step I have to do then is finding rate law by integrating this. Let's assume we run our reaction in a stoichiometric sense. Let us assume for now that the concentration of A is the concentration of B. After all, if we have a reaction of A reacts with B and we want maximum output, then you better have the same amount of A and B to react. And so then I can simplify this one here, that the rate is some K times the concentration of A squared, because B is the same as A, and then and that becomes minus d concentration of A by dt. Now, if that is the case, then I have really a differential equation over here. Differential equation, separation of variables, so I have minus k dt if I bring those things on one side, and on the other side I have 1 over a squared dA. And then I can integrate this one right away, and I'll come from minus k. Integrating dt gives me t, putting the limits t and t0 into it gives me t minus t0. And over here, integrating 1 over a squared gives me minus 1 over a. Putting in the limits gives me minus 1 over a minus 1 over a 0. Okay, so if I have that, then I have essentially the formula for the concentration of A. I just need to rearrange the numbers a little bit. So if I rearrange the numbers, I'll first see, okay, there is the minus sign everywhere, so I'll just get rid of those minus signs. And then I have k times t minus t0 plus 1 over the concentration of A. Initially, it is 1 over the concentration of A. And if this equation holds true, also the flipped one will hold true, that the concentration of A is 1 over kt minus t0 plus 1 over concentration of A. 1 over is something which people usually don't like, so people would rather write concentration of A initially times the concentration of A times k times t minus t0 plus 1. Just getting this one out here from the double. Okay, so I get the rate of the concentration of A. Now, if I didn't have the concentration of A being the concentration of B, then there might be two reasons for that. There's a trivial reason why when that is not the case, and that is if we are looking at the reaction where A reacts with A, if we had a reaction where A plus A becomes C, there's no B of course, then this one here, R equals this one here, that holds true. This one here doesn't hold true anymore in that case. If I have this one over here, then I have the problem that I have here the change of the concentration of A is now twice as big. If I have 1 times the reaction proceeding, I have actually 2 A's consumed. So I need to have my stoichiometric coefficient over here, if there is a small a, that would be 2. I need to have this 1 over a factor over here. So I really need to have a 2 over there, correct? And then people very frequently would multiply the 2 over there and say, oh, I really have an equation which would look 2k times the concentration of A squared is minus d concentration of A by dt. And then people would say, oh, if there's 2k over here, I'll just call this one here my new k. And now we are in trouble territory, because if you're looking up, is there a k for that reaction, you have to figure out, is this actually the k, this k, or do people mean that k? And there's lots of confusion if you look up k's in the literature. very frequently people combine this k times the stoichiometric coefficient into a new k. And then everything starts depending on whether they do that and how they wrote the reaction, because I can write this reaction also both as 2a goes into a C, or I can write this into a reaction as 1a makes 1/2 C, correct? Both ways I can write that reaction. And if I assume one or the other, I get the one or the other result for the rate equation. So there's lots of confusion which can come about in that fashion. And you need to be always very, very careful that you understand what people mean with the case they present. And I'll try to be careful in this class by telling you what I mean with my case when I'm assigning you a problem. But this class is not about you solving my problem, this class is about you being effective in the lab. And so whatever standard we might define here for the class isn't really the relevant thing. The relevant thing is that you have to be able to deal with either way of understanding kinetics and dealing with it as realizing that when you are getting a K, there's a way that you have to look up what that K is for, and B, that you deal with it appropriately within the formulas that you have. And so that is really important. Okay, now, the other complication would be if we were not having the same concentration of A and B in the beginning. And I can tell you that mass is beyond difficult. You have to do many, many case foldings and very, very complicated integrations if the concentration of A is not the concentration of B. There is just no easy way of integrating that. That is a quadratic function, then an A, or 1 over a quadratic function. And so only limited real solutions are available. Most solutions are complex numbers, which of course from a chemical perspective doesn't make any sense. And so you would need to get all the real numbers out of that in some way or another. And that is mass you don't want to do. But if we are working with Excel, then of course we don't have a problem at all. If we are working with Excel, we would now do the same setup as we would have otherwise. We would have, say, in the beginning, here 1 mole and 2 moles per liter, and then we can figure out what is our dA and our dA in such a reaction. That will of course be minus sign because it's being consumed. Whatever K I have, let me define K over here first. So let me define K over here for my reaction. Let me call this H1. And then I would have this is minus sign, and then my K, and then the concentration of the one times the concentration of the others. And here you see that I still need a time step to make this work. Obviously, time step, my time step here can be 0.01. I should not forget my time step to multiply into it. And I need my index, which starts with 0. K times the K times the A times B times times then the dt. And that is of course the same amount as the A, was 1A and 1B, being consumed in unison. And then I know that this here has to be this plus whatever change I have over here. I can pull this over to this, pull that over to the side. And I can figure out here that these ones are still defined in the same way. And I get my concentrations of A to B right away out of this. So I could plug this over here and get my concentration A, and then I can maybe insert this into the graph. Will work or will not work. And here we have the concentration of B, and you get it. Without, ultimately the A will run out, B is still present, but there is then no conversion anymore. If you were to look at what is the change of the concentration, then if this were the graph, changes of the concentration, then you would get the changes are both the same. A and the B are both the same. You can't see two graphs because they are right behind each other. But the reaction stops after a short time. There is barely any change anymore because A is clearly being consumed up and there is no A left, and so the reaction cannot proceed. But finding an analytical formula, finding a formula like I did it on the board over here for that is well made impossible. So using Excel to figure out what your reactions are is a way more productive way of going about it. It is, however, not necessarily what you'll find in textbooks and not what you find in the subject GRE chemistry if you want to go to graduate school. And so we need to deal a little bit longer with ways of not using Excel and figuring things out just because you might be tested on it by other people than me. And so it's important for you to realize all the thinking that has been going into evaluating kinetics in a non-numerical fashion. I should also say Excel is of course not the only tool that you can use to integrate equations. There are more two tools more geared towards doing math for science like MATLAB, where you could do that in. And then there are also specialized tools for kinetics, which you could employ for that. But all what they do is the same thing as what Excel does over here. It is just doing these additions here, numerically integrating a differential equation. Whatever software you're doing, behind it, under the hood, behind the front end, it is doing exactly what you're doing over here. There's just no other way. And so, if those problems, softwares have problems, then you can also see the same kind of problems in this. Okay, then that is what I wanted to say to about second order reaction. Really, Another slide which I stole from my Chem1 lecture, which you probably saw. We have first order reactions. And in the first order reaction, if I want to identify concentrations are a part of the first order reaction, then what I have to do is I can plot the concentration as a function of time on a logarithmic scale. What it says over here, I'm plotting ln of the concentration of A. In reality, nobody would plot ln of the concentration for A. You would plot the concentration from A over here, and then tell the software make that plot logarithmic. It's a very easier way of dealing with that. So you just check the logarithmic button for this axis, and then you will get ln A. And if you do that, and if it was a first order reaction, this first order reaction had this exponential function, or this logarithmic function over here, then you'll find that you get a straight line where the slope is minus the rate constant. And the y-axis intercept is quite naturally the initial concentration, and times zero you have the initial concentration. So you will only get a straight line and not some curve if it was a first order reaction. So the conventional test for figuring out did I have a first order reaction is plot on logarithmic y-scale, put on the x-axis the time, and see that it becomes a straight line. In reality, you would probably just ask Excel to make a fit of the exponential and see whether it works. And we're going to talk about that on Friday a little bit more, what we will read. But that is a conventional wisdom of doing it, and you need to learn it because people might quiz you about it. Then we can have a second order reaction. And in a second order reaction, you plot on the y-axis 1 over the concentration. Now you really have to calculate what is 1 over the concentration so that you can plot it on the y-axis. There is no simple checkbox for that. And on the x-axis you plot the time. And doing that, you then get a slope, and that slope is k, and if it's a straight line, it was a second order reaction. If it's not a straight line, then it wasn't. And it doesn't matter in this case whether it was a second order reaction like A plus A, or whether it was a second order reaction of A plus B type. The only difference you're getting is for the K with this factor of 2 being in there or not. But it will be a straight line no matter whether it was A plus A makes C binary reaction or A plus B. You always get a straight line if you plot it that way. Lastly, there are zeros ordered reactions. People usually don't talk so much about them. They're kind of tricky. Zero order means the rate of the reaction. The rate of the reaction is K times A to the power of 0. A to the power of 0 is 1, so it's K. So the rate of reaction is constant. Every unit of time, you have the same amount of conversion. No matter how much A you have. No matter how much A you have. It's a weird kind of reaction, isn't it? But at the same time, it's a technologically quite relevant reaction. Very often, it depends on an amount of catalyst, how much reaction you can go. The catalyst might be blocked and has a certain turnover frequency, and you get the catalyst doing its business, and if you have twice as much catalyst, then it could do twice as much business. It could do twice as much conversion of reactions. So if a reaction depends only really on the concentration of the catalyst, then in the reactant it is zeros order. It doesn't matter how much reactant you have as long as it's more than the catalyst. that will always be determined by how much catalyst you have. And so you have a zeroth order reaction in the reactor. You might have a higher order reaction in the catalyst. Sure, but in the reactor you have zeroth orders. Then you could think about a reaction where you keep dripping into your reactor, into your beaker, or wherever you do your reaction, at a constant rate some reactant. And that reactant is immediately turned over into the product. Then the formation of the product or the consumption of the reactant is determined by how fast you drip it into your reactor. And if you drip at a constant rate, then your reaction will proceed at a constant rate. And you would also get a zeroth order reaction. It doesn't depend on the concentration, it only depends on how fast you drip. If that is constant, then it's independent of the concentration. So there are many scenarios in which you can imagine in which you have a zeroth order dependence. They have nothing to do with molecularity. All those examples I just gave had to do with how do you run the reaction? How do you proceed the reaction? So kinetics has to do with both how do the molecules rearrange themselves, how do the molecules interact in order to allow the reaction to go, and how do you as a chemist run the reaction, provide catalysts, provide reactants, heat, cool, have your glassware set up in whichever way or whatever you're doing. Both of them affect the rate of your reaction. Both of them affect the kinetics. And if we talk about order of a reaction, then we take everything into account. We take into account how do the molecules interact with it, and also how do we run our reaction. But if we talk about molecularity, then we only think about how the molecules interact with each other, not how we run the reaction, how much reactant we provide, how much catalyst we provide, and so on and so forth. So for that reason, there is a difference between the unimolecular reaction and the first order reaction. First order something can be because that way I run my reaction. For instance, if I were to have a reaction between a solvent and a reactant, like for instance, I would put very slowly some hydrochloric HL gas or hydrochloric acid into concentrate hydrochloric acid into water, then you will of course see the dissociation of the hydrochloric acid right away, almost quantitative. But the rate at which that proceeds depends only on the amount of hydrochloric acid I have available, not on the amount of water, because water is a solvent and there's always infinite, always 55 moles per liter of water there, no matter what you're doing really, as long as you don't have exceedingly concentrated results. So it doesn't depend on the concentration of the water, because there's always so much water that it practically doesn't change. And again, you would observe a first order reaction out of this one, because it only depends on how much hydrochloric acid you put inside. But the first order comes about by the solvent, the other reactant, having constant concentration no matter really how much you react. And you get a first order reaction, even though it might be a bimolecular reaction, which is going on. So again, order depends on how we run the reaction in combination with how do the molecules interact, whereas molecularity doesn't. So if I have a zeroth order reaction, then the concentration will go down at a constant slope of time. If I have always the same amount converted per unit of time, then the concentration will change linearly. And I have the most simple of plots with the time on the x-axis, then the concentration on the y-axis. Not logarithmic, just the concentration. And I have a formula like this zero order reaction. So, if you make 3 plots of your concentration or something about concentration as a function of time, and you figure out which one of these plots is the most linear, then you'll have a good idea what order of the reaction you have. And then you have to think about whether that order came about by how did you run the reaction or by how did the molecules interact with each other, and then you can deduce from that whether you had a first order, a unimolecular or bimolecular reaction, whatever else is relevant. Okay, so this point, I'd like to quiz you on what we just said, because those kind of quizzes will be everywhere in the chemistry life on these kind of reactions, even though in reality you can do many things. Okay, so let's do it. The zeros order rate law results in a linear dependence of the concentration on time, an exponential dependence of the concentration on time, and a logarithmic dependence of the concentration on time, on linear dependence of 1 over. Come on, we just had it. We just talked about it. Okay. And the linear dependence, yes, of course, that was the straight line on the right-hand side, the really simple case. Okay. In a system of competing first-order reactions, with the constant K1 is 2 Hertz and K2 is 10 Hertz, there will be the same amount of product of reaction 1 and 2. There will be more of the product of reaction 1 or more of the product of reaction 2. Competing reactions we had in class last time. One rate constant, reaction 1 is 2 Hertz, the other one is 10 Hertz. Where do we get more? Okay, and most of you will are right. If we have a higher rate constant, then that reaction will be faster. Then you remember, I hope, oops, I saw it a moment ago. I guess I ran out of internet connection. If I have a higher rate of that reaction, I will get more of that product. You also remember probably last time in class we had those prefactors KB over KF plus KB or K1 over K1 plus K2 and so on. Those factors are where it comes in. Now if I give my rate constants in Hertz, Hertz is just a fancy way of saying 1 over second. It means I have a unimolecular or first order reaction. It really means I have a first order reaction. I know that my rate has to be 1 because my rate needs to be moles per liter and second, or some other unit of concentration per second that is being converted. And this one here is moles per liter. If this is moles per liter, then this is 1 over second over here. If I had a second order reaction, then I would have moles squared over liter squared over here, and my rate constant would need to be liters over mole in second to make it, again, to a rate which is always some concentration per second. So from the way I posed that question, you could also deduce that what I got out of this one here and it seems all everywhere. Let's see, does it work? Did we get it working? Okay. Last one. Oops. So much display. The molecularity is the same as the order of a reaction. It's only defined for an elementary reaction step. It's defined for any reaction. It's particularly important for reactions involving 4 molecules at the same time. Which of these ones is correct? Okay. So, it's only defined for an elementary reaction step. That's the correct answer. Most of you have that. It is not the same as the order. We just talked about many different cases where the order is determined by how they run the reaction as opposed to what do the molecules do. And it is not defined for any reaction, the molecularity, because if I have a really complex reaction which involves many different elementary reaction steps, then I can't say there's only one molecularity of that reaction. There are many. And this one here is particularly relevant for reactions that involve 4 molecules at the same time. Here's a really big problem. If I have one molecule, then one molecule can decay. The unimolecular reaction, I get a first order rate law out of this one. Okay. Second one over here. 2 molecules hit each other. That will happen. I can get a rate law out of that by K times the concentration of the one and the other species. Trimolecular reaction. You know how fast those molecules dip? Is it really likely that 3 molecules happen to hit each other all at the same time? Presumably it can happen, but it's already really, really rare incidents. So probably it will not happen. It is at least slow reactions. And 4 molecules happening to hit each other at the same time is well near impossible. Don't worry about it. It will not happen. Or it will happen, but only to an amount that it is from a mechanical perspective completely irrelevant. There's also lots of steric hindrance. Do they actually even fit to each other so that they can hit? So there are no tetra or quadrimolecular reactions. There are unimolecular, bimolecular, termolecular, or trimolecular, but really no tetra or quadrimolecular reactions. You don't need to worry about that. What we're going to talk about on Friday will be chiefly if we have reactions where we have steps going one after another. And in those reactions, how do we then come up with the order? And what do we do in such cases? That will be the subject for Friday. Before that, let me assign you the homework. No, this is no bonus homework. We have had 12 homeworks. The 12th homework was submitted today. Every homework which I'm assigning starting from now is just bonus. Yes, I should post that slide because that's what so it is essentially doing the same thing which you did for homework for successive consecutive reactions now for bimolecular one. I'll post that slide right after getting back to my own. So there's a homework, but it will only substitute for any of the previous homeworks you either missed or weren't so good in, and it is not a required homework anymore. All the